All right, our last and possibly the best talk for today in this venue is Matheus Castello from Toradex, talking about using Debian containers for cross-development with some real-life action. We look forward.
Thank you. Thank you for attending. We will talk about using Debian containers for cross-development. I will talk about some challenges we have to cross-compile native code for embedded systems, right? I am show some solutions that already have to solve these challenges, okay? And using Debian containers at the end for solve this challenge too, right? So I'm Matheus Castello. I have 28 years old, not in appearance, right? But but I have documents to prove it. If you have to, if you can see. And I am embedded software engineer and Toradex here in Brazil. I work with a marketing team, technical marketing team here in Brazil. And in my spare time, when I'm not working with embedded systems, I'm working with embedded systems too, with contributing with open source projects and make these lectures, right? So this is who I am, and I have to know about you too. Who here are desktop developers? Right, and embedded systems developers. Oh, I have a good number. It's a good. I can go fast some points. Okay, so go forward and we'll talk about development challenge for embedded device. So let's get started with an example, a hello world example, right? I have a simple, very simple hello world example here. Let's get, it's the simple print with hello, right? So in your development machine, we can easily compile this hello.c, right? And run. Right, no problem. Here I have two on development board, right? That's running and is based in ARM. Is a bit small. It is that. Let's get. Oh no. Let's change the font here. Okay. So we have a development board here running ARM v7 processor, right? It's or the embedded device. So if I get that program here and copy this, Horizon and my address. Oh. Right. And try to run this logical. This is not run because I'm compiled this for my architecture from my notebook, right? Is as if we check the file type from my hello binary, here is an executable from x86 architecture, right? So this is one challenge we have for develop cross-develop for embedded device. Generally, we have a computer that have a different architecture than the architecture from our embedded device. So we need some program, some compiler that runs in your architecture, on your development architecture, and you generate a binary code with instructions that will run in your target device, right? So how we can solve this? We have the Binoculars package, right? The Binotius package have alt toolchain, the GNU compiler and linkers. And if we install the Binotius, only the Binotius with no these other names, they will install the compilers and linkers for the architecture from my host. But we can install Binotius for other architectures too. Here we are using the Binotius ARM Linux GNU API hard floating. It's already installed here. So I can cross-compile this. Right. And if we check this, now we have a binary with the ARM architecture, right? And with lucky, we can, here. Copy, and this will run. Now the processor knows the type of instructions that we have in this binary, and the processor can run this binary, right? We have the hello DebConf running in your embedded device. So, problem solved. We have some guy, some compiler that cross-compile the code for me and generates ARM v7 code that runs in my target device. But a hello world is a very simple program, right? Let's try an example that use a library. And here we have the hello blink. It's okay. The hello blink used the libgpiod library. So we have some instructions and some functions that request the GPIO banks, GPIO pins, and request the pin for output. And I'm here doing a while that is changing the logic value of my GPIO at between 1 and 1 second, right? Okay, let's try compile this. Now we have a cross compile. Let's generate the blink. Compile the blink here. Hello blink.c, and tell the compiler that will link with the GPIOD. Oh, we don't have the dev package for this guy. Okay, let's install it. libgpio, libgpiod, dev. Okay, installing, install it. Let's, cannot find why. When I install this package, the libgpiod dev, we are installing again on package that runs in your development architecture. So I install libgpiod for x86 architecture. I need the ARM shared object for this guy, for the cross-compile, compile and link with this shared object. So we have this guy, the Debian package, add architecture for our target architecture. So I'm already done this in my computer, and we can install now libraries with this parameter, and we will install the libgpiod for the architecture of our target device, right? So apt install libgpiod dev for ARM hard floating. Okay. Okay. Now it's all right. We can compile, cross-compile, and link with the shared object for ARM. And with luck, this will run in our embedded device. Let's copy this guy. Oh, why? I lost the connection? No. So let's run this guy here. Oh, okay, all right. We installed the library and shared the object in my computer, right? How we can solve this? Well, I can copy the user lib arm. Oh, here we have the shared object for libgpiod. We can copy these guys from my target device, but this is not a smart way to do it. Okay. So we have other solutions more smart to do it. Think about on the project that we have a lot of dependencies, a lot of shared objects. This will end in a dependency hell, right? And you have to make some script to copy this from your host, from your or target device, and it's not the smart way to do it. So we have other solutions for do that. One of this is the Octo project. Octo builds your own Linux distro, and we have some layers that bootloader and kernel, the board support packages. These layers are provided by the vendor of your hardware. You don't have to care about this, but the user space is on a layer that we have to work. Put the packages we need, the libraries, and everything we need to run our application. The Octo is based in recipes. We have to write these recipes to configure all the needs you need for your application, right? And the pro is you have a distro optimized for your hardware. But the weak point is the learning curve. You have a high learning curve to make these configurations, these recipes with the Octo project, right? Other solution is the ChangeRoute solution that you can create, copy, and configure your sysroute using the ChangeRoute, right? You can use a radio ARM architecture distro as base, right? I have one here. I have a Debian base that I unpack where? Here. So here I have the root file system from a Debian base image, right? That image is from ARM64 architecture, ARMv8 architecture. So I can run this, the ChangeRoute here, passing this root file system, and we have a distro running for other architecture here. If we run arc, whoa, how is it possible? Because Tcemu, right? We have Tcemu arc64 for ARM static running inside this ChangeRoute. So Tcemu is translating out instructions from the ARM architecture form or x86 architecture, right? So here in this root file system, we can run out or Debian commands like apt update, apt install, and everything. That is not working. I'm not copy and make the symbolic links for my local conf. This is it, but no problem. So with the ChangeRoute, we can configure all that things, install the compilers, install the libraries that will install for the ARM architecture. So we can use the GCC sysroute argument and pass this folder for GCC to compile and cross-compile our applications using the root file system that we configure in ChangeRoute. Okay. One weak point is it is not so easy to deploy and document and duplicate this. We have to write your own recipes or one scripts to make this part of deploy, document, and duplicate. The guys who make work with Raspberry Pi use this a lot because it's very easy. We have all the system running in an SD card, so we can get the SD card, put in your computer, and change route to a root file system of the SD card. So it's an easy way to do it, right? And other solution is using Docker for package isolate and dependence of all the dependencies of your software or of your application. This is the a pro point of the Docker's containers. It's easy to deploy, document, and duplicate. The thing we don't have with the ChangeRoute, right? It's a standard way to do these things with the Docker containers, right? So what is a container? No? We have the ship that is the kernel, right? All these packages, all these containers are software packages isolated from each other, but we have a shared kernel, right? This is the definition from Docker website, a package software into a standard way units for development, shipment, and deployment, right? This is what the Docker website. We have today Linux and Windows containers that can be deployed in data centers and cloud, but this is changed. Today in the market, we are seeing developers making these containers, deploying these containers at the edge with in embedded devices, right? Here are a bit of the differences between a container as an application and a virtual machine, right? In a container, we have only the user space, right? Is isolate out each process, each package is isolate from each other. We can run the Debian 8, Debian 9, Debian 10 in each container of this, and they share the kernel, right? In a virtual machine, for do this, we have to virtualize all the thing, the user space and the kernel space and all the infrastructure. Okay. So we can run a Debian 10, a Debian 8, and a Debian 9, but all is virtualized, and the kernel too is virtualized, right? So the container is a nice way to do a virtualization. It's not virtualized, but I can say this because we are running, and user space is a process that are running in C groups, right? And they isolate from each other, but we are using the same kernel, and we have to take care about it. If we are accessing, for example, the hardware from one container, this is not isolated from the others. Okay, so we can crash the kernel. If you crash the kernel, you crash all the others containers too, right? And here, only for curiosity, is the way the Microsoft run Linux containers. The Windows don't have the kernel Linux yet. They are launching a new version with something to solve this. But what we have, they have to virtualize a Linux kernel, and all the containers run inside this Linux kernel virtualized. This is the smart way to do it, but it's a water way that they virtualize all the thing, not only the container, not only the kernel, but the container and the kernel is inside a virtualized. It's like a virtual machine. It's not changed. So in Windows we lost this lithe way to deploy a container, right? It's not a smart way to, not the best way to use containers with between Windows. Okay, so let's do the same examples we do for cross development with our native cross toolchain, but now with containers, right? First, we need the recipe, the Dockerfile that will say what have to be done for my application. So, for the hello example, the hello world example, we have this Dockerfile. It's okay for this thing, well, okay, more or less. All right. Okay. So here I have the Dockerfile for the hello example, and here I'm running 2 stages. I'm running a multi-stage Dockerfile, right? The first stage I call it as build, right? And this is cool about the Docker containers. We can use other image as base. So I'm using an image here, the Bnucius Debian, that is described here. So here I have an image from Debian Buster's link, right? From the ARM v7 architecture. And I am running, this command will run a command, the apt-get, blah, 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 with all the packages that I need to compile stuff in my container, right? So I made one generic container based in Debian Buster's link ARM v7 architecture with all dependencies for toolchain. And I can use in all my projects that I need to make native compilers for ARM v7, right? So here I'm copying the hello.c source. What?
Can you please repeat the question?
No, no problem. Good.
I'm lost now. Which architecture is this Docker container running on? On your host architecture, so Intel or ARM? And if or on ARM, then how do you run container on ARM architecture on Intel?
Here I am using the image as base. Okay, this image is for the ARM architecture, right? And the build I will run in my development, my notebook. That is an Intel architecture, right? I will get it. I will reach this step, right? More forward. Okay. So we have an ARM v7 base image, right? That we will install all the packages for toolchain, and here I'm using this base image, right, for compile my program. So I'm copying the hello.c source from the folder from my source and copying to my container, right? This is what copy do. And I'm running the GNU compiler, generating code, generating the binary from my hello.c. This is the first stage. Okay, here I'm only describing what Docker will do in the build stage, right? Now we have the second stage. From a Dockerfile with multi-stage, the last stage is the stage that the image will be built, right? So in my second stage, I'm using Debian Buster's link 2 for the ARM v7 architecture as deploy. But here, I'm copying only the hello generated, program generated from the other stage, from the build stage, right? That's what I'm saying here from the build stage, right? From the build stage to my target, right? And I'm running command hello to run this command inside the container, right? Here I'm only describing this. Now I can build this guy, DebConf. So we need the Docker runtime running, right? I have here the Docker runtime running. And I will Docker build file, Dockerfile. Here I'm passing the folder that we will use as reference for the Docker runtime, right? This is this folder, temp DebConf. And I will pass a tag to name this guy, DebConf, right? I'm already done this, and Docker build works in layers. So for an image, we have a lot of layers with all the steps of the Dockerfile described, right? So for deploy this, we can make only the delta, only the diffs from the layers, and only download the different layers for an entire image, right? Okay, successfully. Now we can, oh no, first we have to push this. So I will push this from my my computer to Docker Hub, right? I'm pushing this image to Docker Hub cloud, so I can pull the image in my embedded device, right? I'm forget one thing. When we do this, the Docker runtime will run these commands, right? Will compile our program, right? In an ARM v7, like ChangeRoute do, using TKIMO. We have this service here. This guy will run, will translate the instructions, right, from the ARM for my computer using the TKIMO static program, right? So this will run in a way like we do with the ChangeRoute, right? So at the end we have here the hello for the ARM v7 architecture, right? That's it. Okay. Now in our embedded device, here in our embedded device we have Docker. We have Docker runtime too, right? Right. So we can pull this image in your embedded device. Matheus Castello, DebConf. Downloading. Image is up to date. No changes from my image. So now we can run. Oh, let's see one thing. Docker image that I have installed here. I have this image here that have this amount of storage, right? Spent. But if we have here in our development computer, I will grab this. It's the same image, right? Same amount of storage. But what I have to show is this one guy. Whoa! For an embedded device to deploy this on an embedded device, it's a lot of storage. So this is a good cause to run the multi-stage Docker build, right? We don't need all this stuff here. We only need the program and run the program, right? Okay. Let's run this. Docker run. I will paste this argument to remove the container of the end of running, right? And this will be interactive, so we can see the output. With the lucky, okay, so we are running our hello.c program in a container inside our embedded device, right? In ARM architecture. Here is not native. Here, right? So we do all these stuffs. We have the Dockerfile with the describe of
Forgive me, I'm just a little bit confused about how QEMU works, because I know that QEMU can emulate other architectures. So you're running a Docker. Usually when you have a Docker, the Docker will use your own kernel. And in this case, the QEMU will have a kernel from itself that it's going to use to run the Docker, or?
No, they are using the QEMU static, the QEMU user static.
Okay, so the QEMU will only translate the user space to your own kernel.
Yeah, it's not all virtualized. No, with this the service, the Beam format do it for us. Because, for example, we have the hello here. The hello is compiled for ARM, right?
Yes.
I can execute it because the Beam format.
This Beam format?
Yeah, this service here. This service here get the header from the binary, right? And then get the type of the architecture from the binary, and calls the QEMU and make the calls inside the QEMU, right? So they translate and run in my architecture.
Okay, it's just that I understood, but I'm still a bit confused. How come you can translate user space and calls to kernel space from ARM64 to then x86, and that just works? And I don't know. I'm just a bit confused on how that works.
Yeah.
It's all right.
Yeah.
I got the image.
I don't know response with the technical part of this, but the QEMU user is static. It runs this translation. And I believe too. Right. So we have the Dockerfile with the describe of our comments, right? What we will have, the needs for our application. So this we will build an image, a Docker image with our Debian container, and we will push this to the Docker Hub or other cloud with a Docker registry. Okay, so we can at the end pull this image on our target device and run this in our target device, right? Let's do the blink example too. Only for the fun to see a LED blinking. And the Dockerfile is a bit more with more steps. Here we have the same concept of the other Dockerfile, right? We have a build stage, right? But here we are installing the libs that we need, right? We are using the Benutil's Debian that I described in the other Dockerfile, in the other Docker image, right? And I am installing here the libgpiod and the libgpiod dev readers. I'm copying the source, right, and compiling and linking with the libgpiod. And again, we have the stage of deploy. here in deploy, we already have the blink linked. We don't need the libgpio dev. We only install the shared objects package, right? So I copy the binary, and at least we will, at the end, we will run the blink. So first, we have to build it. Dockerfile blink from this folder reference and tag as Matheus Castello, DebConf blink. Okay, it's already compiled too. You can see the layers here. No difference from the layers. We can now push the image. Matheus Castello, DebConf blink to the Docker Hub. To checking the layers, no difference from the layers. And now we can deploy it on the device. It's not difference from the layers, okay? The image is up to date. And now we will run this image. DebConf blink. Oh, only the hello DebConf output. Why? We have here the code, the hello DebConf, the access to, we are access the hardware. So I can have to tell the Docker runtime to that container will access the hardware. So I have to Docker run, remove it, interactive, and pass this one, privileged. Okay. I will type this from here. No, it's not a good idea. I will did it here. Docker run rm it. I have to tell Docker that this container will run privileged commands, right? So, and we have to tell him to access the hardware too. The libgpiod use this. Oh. These guys. The libgpiod use these devices guys to access the GPIOs, right? So we have to tell the Docker that dev volume is shared between the container and the host device, right? With this argument volume, we are mounting the dev shared between the container and my host from the target device, right? And the Docker image. Okay. So, with lucky, we can run this. Oh, you are seeing here? It's blinking. Oh. Right? So this is a kind of thing we have to take care about, because we are accessing a device that is mounted from our kernel, for shared kernel. So we can do something if we are accessing other things from our kernel. We can crash the kernel and crash all others containers that we are running in our target device, right? So this is it. And one weak point that we can see from the Docker images for embedded device, it increases storage memory span because we have Ulti-root file system from my device that is running the Docker runtime, and we have the container root file system from our Debian's containers too, right? So we have to think about this storage memory that we are spending. If okay, that's it. This is very simple examples, but I'm using containers to build Qt applications that have a lot of dependencies, a lot of shared objects, GStreamers, Wayland, GTK, and .NET Core. This is some projects that we already build CrossCompile from for our ARM device with using containers. So that's it. If you have some questions, so take it easy.
Thank you, Matheus.
What is the size of the Docker runtime in the target platform?
And Docker platform is a good question. I don't know precisely, but we need a Linux micro platform, right? With a root file system, with libc and everything for running your Docker runtime. All this image.
The Docker runtime, like the Docker.
Yeah, I don't know the size of the Docker runtime. I know the size of all this image.
So if
is more or less 600 megabytes.
600 with Docker?
Yeah, with all the file system.
If you have an image with Docker, which size is that? And if you take Docker out of the image, how much is the size of the image?
The image we can see here. The Docker images.
Not the Docker image. The runtime at the target. The memory space that uses. Okay.
Basically, the question is how big space are you using on your embedded devices to have everything that is needed to this Docker? So Docker runtime, all management, all the libraries that are used by Docker, all those layers that are translating those host instructions to guest instructions and so on and so on. So how much do you additionally using on embedded device?
Right. More or less 200 or 600 megabytes. Right?
Any more questions?
Right?
All right, thank you very much.
Thank
And
you,
that
guys.
concludes the first day.